Yes. Okay, now. So the third, we considered the three conditions, and now the fourth, the three conditions were: first, the primary and secondary winding does not have any resistance. Second condition is there is no leakage flux in the magnetic core, and the third condition is VH curve is linear. And the fourth condition for the ideal transformer, which we will consider, is that there is no iron loss in the system. Now, what is this iron loss? Basically, due to the non-linearity of the VH curve, iron loss occurs into the system. We will discuss this later, but right now you will have to consider only fourth condition. So the fourth condition, the four conditions which we are considering here is: first, this is listed here. There is no resistance, there is no leakage flux, the VH curve is linear, and the fourth one is there are no core losses in the transformer magnetic core. So with these four conditions, we are moving ahead with our ideal transformer. And first topic which we will see here is that is the EMF induction and the phasor diagram. And this will be dealt in the two format. In two parts we will see. The first portion is the transformer at no load. Transformer at no load means we are not connecting any load to the secondary winding while we are exciting the transformer. It means we are giving input to the primary winding, but we are not connecting any load on the secondary winding. So to show this, we are showing one switch S over here. In the diagram, you can see over the screen, switch S, which is open. So open means this load ZL is not connected with the secondary winding. So what would be the impact of it? When we will apply primary voltage on the transformer, when we will apply give input to the transformer, the voltage will be applied. So the primary current will begin to flow. This primary current will establish flux in the magnetic core. That would be an AC flux, and this flux will establish induced EMF in the secondary winding too. But in the sense the secondary winding is open circuited, so therefore there is induced EMF, but there would not be any flow of the current in the secondary winding. So in this situation, when we are applying primary voltage, primary current, primary induced EMF, flux established in the magnetic core, and the secondary EMF induced, these would be the discussion of this part, that is the transformer at no load. So this is in bracket, it is already written switch S is open. Now just see the diagram and we will start with this one. Now consider the situation when we are considering, since we are considering the AC voltage has been applied to the primary winding. This AC voltage is responsible for the production of the EMF, for the production of the primary current in the magnetic core, primary current in the winding. This will establish a flux. Of course, since we are applying AC voltage to AC current, so therefore the flux which will be established in the magnetic core will be of AC nature. So therefore we are starting from here that we are considering that phi equals to phi m sine omega t is the flux which is established in the magnetic core. Why we are considering sine of omega t? Because we are considering that the voltage applied on the primary winding is of AC nature, and that AC means the sinusoidal voltage. So sinusoidal voltage will result in the production of the sinusoidal current, and sinusoidal current will produce a sinusoidal flux. As you know, the flux is directly proportional to the flow of current in the winding. So therefore, the flux which is established in the magnetic core would be phi equals to phi m sine of omega t. Now, you know, as per the Faraday law says that whenever there is change in flux around the conductor, EMF will be induced. So this established flux, this established flux will cause the production of the flux in the primary winding as well as the secondary winding. There is one particular point which is very important to consider here. Here, the EMF induced in the primary winding will be a self-induced EMF. Why it is self-induced EMF? Because it is the EMF induced because of its own flux. So that's why the EMF induced in the primary winding will be a self-induced EMF, while EMF induced in the secondary winding will be a mutual induced EMF. Why mutual induced EMF? Because this is the flux, this is the EMF induced because of the flux of some other circuit. So therefore, since the flux which is flowing in the secondary winding, this flux is produced by the primary winding. So therefore, the EMF induced in the secondary winding will be a mutual induced EMF, while the EMF induced in the primary winding will be a self-induced EMF. So therefore, in the transformer, it is said that there is EMF induced in the transformer because of the self-induction as well as the mutual induction. Both the kind of the induction do exist in the transformer case. So this is okay. Now, as per the Faraday law, our aim objective is right now to find the EMF induced in the primary winding as well as in secondary winding. So therefore, to do this, we will see the Faraday's law, and Faraday law simply gives the formula of E1 equals to minus N1 into d phi over dt. So E1 equals to minus N1 into d phi over dt means this is EMF induced in the primary winding. This is the number of turns in the primary winding. Dy dt of the flux linked with the primary winding. You know, flux linked we have already considered. This is equals to phi m sin omega t. So therefore, we will write the expression minus N1 into d by dt of phi m sin omega t. Mathematically, we will differentiate with this expression phi m sin omega t with respect to the t. So you know, since this phi m is constant, so therefore it will be out of the integration. So the expression would be minus N1 into phi m, and sin omega t will get converted into cos of omega t. And since the differentiation is with respect to the t, so therefore there will be omega. So the final expression which we will receive is equals to E1 equals to minus N1 into phi m into omega into cos of omega t. So therefore we will write here E1 equals to this, and minus we will combine with the cos. Hello. हेलो, आवाज आ रही है किसी की? एक मिनट, I am pausing myself. Just wait a minute. No need to panic. I am here. Okay. So now we will go ahead. So we will combine this minus sign with this cos of omega t, and you know, minus cos of omega t we will write as a sine of this expression, sine of omega t minus pi by 2. As we had already discussed in the class, whenever we need to write sine expression, we will use this kind of the setup. And rest of the portion which is given here, this is this portion, N1 phi m into omega. We will write it simply as a E1, that is maximum voltage induced. So finally, the expression of the voltage which is induced in the primary winding, it will become equals to minus E1 sine of omega t minus pi by 2. So one thing is very clear from this expression, that this induced EMF is going to lag behind this established flux by an angle of pi by 2. That we will see at the time of drawing Phasor diagram. So we will see that one. So now in this expression, we will see here E1 is what? E1 is N1 into phi m into omega. So therefore, since it is a maximum value, you know, this value is the maximum value of this expression, this voltage EM1. So therefore, what would be E1 RMS? So E1 RMS, we will write E1 by root 2. This is maximum value by root 2. So we will write here, and we will replace this omega by 2 pi f. So later on, we will have the complete expression of RMS value of the induced EMF in the primary winding would be given by 4.44 f into N1 into phi m. You can see this root 2 will cancel root 2, and root 2 into pi will yield 4.44. So, so now similarly, we will go for the secondary winding, and in secondary winding E2, the similar expression we will use is E2 will become equals to minus N2 into d phi by dt. We are keeping same flux here, as you know, we had already considered this is the ideal transformer and there is no leakage flux. It means whatever is the flux is associated with the primary winding, the same amount of the flux is also associated with the secondary winding. So on the behalf of this, we will obtain the similar expression, and we will have E2 equals to E2 into sine of omega t minus pi by 2. And here the RMS value of the induced EMF in the secondary winding will become equals to 4.44 f into N2 into phi m. You can observe in both the expression, the only difference is N2, because if you will see the difference between E1 and E2, you will find there is a difference of only N1 and N2. The rest d phi by dt is the same. So therefore you will find this kind of the setup, and this is overall equation. So based on this, we can find this E1 upon E2, and if we will take the ratio of E1 upon E2, it will become N1 over N2. N1 over N2. So this is one. Now it means what we did, we applied a voltage on the primary winding of the transformer, which established a primary current in the primary winding. That established current causes the production of the flux phi, and that phi was capable of, and basically that phi induced the primary voltage as well as the secondary voltage. So now we are in the process of drawing the phasor diagram of the transformer at no load condition. At no load condition means there is no load connected in the secondary winding. So this is the situation. So now we are first drawing this phi equals to phi m sin omega t. Since this phi was associated with 0 angle, so therefore we did it on the horizontal line. And you know, this flux is directly proportional to the current. So therefore, and since we are considering that BH curve is linear, so therefore there is no phase angle difference between flux and current. So therefore, whatever is the direction of flux, the same is the direction of no load current. So this is the no load current which is established in the primary winding, and this causes the this causes the production of flux, and this production of flux causes the two EMFs. One EMF is the primary induced EMF and secondary induced EMF, and both the EMFs are lagging behind this flux by pi by 2, as you can see from the expression. So that is shown in the diagram. And now the equivalent to this one, primary induced EMF, this EMF will be balanced only by the applied voltage, as there is no resistance and no leakage flux in the primary winding. It means whatever is the voltage would be applied to the primary winding, the same would be induced, because it will balance each other. Because under any condition, this circuit will also follow the Kirchhoff's voltage law, and Kirchhoff's voltage law simply says the algebraic sum of the voltage in a closed path will be equals to 0. So therefore, it means the primary winding, if we will apply KVL in the primary winding of the transformer here, so it means if we will apply KVL in this one, so this primary voltage applied and the primary EMF induced, both would be opposite to each other, and both will balance each other. Therefore, if we will have the flux, we have the phasor diagram of primary induced EMF E1. Based on that, equal and opposite, we will have the primary voltage applied. So this is the phasor diagram at no load. Now we will go ahead and we will consider the case transformer at no load. Now this is very interesting and very important portion of this one. And basically this portion, transformer at load, basically explains the actual working of the transformer. Now in this condition, since we are writing this is the condition of transformer at load, it means now we are going to connect load on the secondary side. What would be the impact on the load on the secondary side? To connect load on the secondary side, we will close the switch. So therefore it is written here, switch S1 is closed now in the figure number 1. And that figure number 1 has been redrawn over here with an arrow closing this switch. So therefore the switch is since closing, so therefore the secondary circuit is going to be closed and the transformer is going to work at some load. So when we will, what would be the impact, since you know there is a primary induced EMF E1, there is a secondary induced EMF E2, and circuit is now closed. So of course it is very natural, since there is induced EMF and circuit is closed, so therefore there will be current flow in the secondary winding now. So to understand properly how it will work, that is very important. And let me tell you, this is one of the very important aspects. So please read very carefully. Now what will happen, as we will close the switch, there will be a secondary current begin to flow. Now this current will produce a demagnetizing effect. Now what is the meaning of demagnetizing effect? Demagnetizing effect means if there is a flux around, it will produce flux in the opposite direction of the already existing flux. Means it will produce a flux in the opposite direction of existing flux. Why it will happen? Why it will produce demagnetizing flux? Because you know there is a Lenz law, and it simply says that the effect always opposite its cause. It means whatever would be produced, whomsoever is the reason behind, it will oppose that quantity. So basically here the current gets established in the secondary winding because of the already flux. If this flux had not been here, there would not be any induced EMF, and if there is no induced EMF, there would not be any current in the secondary winding. So therefore, to oppose this flux, current will begin in such a way in the secondary winding. So to oppose, so it means, so therefore to oppose already existing phi flux, the secondary current will produce a demagnetizing flux of phi dash. Okay, so as phi dash will be produced, this will reduce the amount of the flux, and that will cause the overall reduction of the flux in the entire core, and entire core will cause the reduction of the flux in the primary winding as well. So it will reduce the, since the flux established in the magnetic core is dropping, so therefore E1 will also drop, because E1 is what, minus N1 into d phi by dt. So if the flux established in the magnetic core is going to drop, it means the EMF induced in the primary winding is also going to drop, and this drop will cause the difference between the V1 and E1, because V1 is what, applied voltage. This is not going to, it is not going to change, but E1 is what, induced EMF, and if the flux will reduce, that will cause the reduction of E1. So if E1 is going to drop, it means it will increase the gap between the B1 and E1, and if the gap between the B1 and E1 is going to increase, that will cause the more amount of the current flow in the primary winding. So finally what will happen, so it means the primary voltage will be responsible for maintaining the flux in the entire magnetic core. So therefore this will produce an additional current I1 dash to neutralize this phi dash. So therefore whatever is the demagnetizing effect of phi2, the same amount of the additional magnetizing effect, additional current I1 dash will be produced in the magnetic core, and finally the net current in this one. So whatever is, I'm sure, I think ज़्यादा लोग समझ में आएगा, but to make you understand, I wrote each and everything in this notes, so you can read from here. As a result, current I2 gets established in the secondary winding and produces demagnetizing effect. Now question comes, why demagnetizing effect? So the answer is because of the Lenz's law, which states that effect opposes its cause of production. So since flux is the cause of production of current I2, therefore I2 produces demagnetizing flux phi dash in the magnetizing core. To maintain constant flux, primary applied voltage produces additional current I1 dash in the primary winding to nullify the demagnetizing effect of I2. I hope everyone is very clear on this. And one more thing is here, if the additional current I1 dash is here to nullify the demagnetizing effect of the secondary current, therefore this N1 I1 dash, which is basically what, the nullifying MMF established in the secondary winding because of the load one, and this is the N2 I2, which is demagnetizing MMF. So therefore N1 I1 dash will be equals to N2 I2. So additional magnetizing current, this is demagnetizing effect, both will be equal, and this, so it means this I1 dash, additional current which is flowing in the primary winding, this is basically produced because of the load connected at the secondary. If we had not connected load at the secondary, there is no need of this I1 dash. So therefore this I1 dash is known as the load component of current. This one is known as the load component of current. And therefore, since it means now the primary winding will have two kinds of the current. One is the no load current, which was responsible for the flux production in the magnetizing core. And I1 dash, which is established in the primary winding, that is basically the load component of current. So therefore the net current flowing in the primary winding will now be equals to the I1, and that will be equals to I0 plus I1 dash. मैं आप सभी लोगों को एक मिनट के लिए म्यूट कर रहा हूँ just to get the feedback that everyone is finding this one and understanding. Just to have your feedback, I'm muting everyone. Shwetank. Manchan. Shivam Tiwari.
Yes, sir.
Shwetank कहाँ चले गए भाई? श्वेतांक, आवाज मिल रही है? श्वेतांक, आप लोगों को आवाज मिली पूरी? आप लोग समझ में आया पूरा? श्वेतांक, आप समझ में आया पूरा? एक डाउट?
Yes, sir.
आवाज मिल रही थी आप लोगों को प्रॉपर?
Yes, sir.
ठीक है, तो मैं आगे कंटिन्यू कर दूं ना?
Yes, sir.
ओके ओके ओके। Okay, so now the net primary current will become equals to I1 plus I0 dash. I1 will become equals to I0, which is no load current when there was no load, and I1 dash is the load component of current. Generally, if we will see the full load current of the transformer, you will see this is just this no load component of current is only 2 to 4% of the full load current, while the full load component of the current is contributes 96 to 98% of the net current. So on this behalf, we can conclude that this primary current is approximately equals to load component of the current. Though no load component of current also plays very important role, but we will discuss. So on this behalf, we will go for the approximation, and on the behalf of approximation, we can say this I1 net primary current is approximately equals to the net load component of the current. So therefore, this formula can be established that N1 I1, earlier we had written just above, this one was N1 I1 dash, that is equals to N2 I2. But now this at I1 dash we are removing and we are replacing it by complete I1 because of this above approximation. So therefore N1 I1 will become equals to N2 I2. And from here we can say that N1 over N2 will become equals to I2 over I1, and I2 over I1, that is on the behalf of N1 over N2, we had already written N1 upon N2 equals to V1 upon V2. So this formula can be established, and this is called the transformation ratio. And from on the behalf of this portion, we can write this V1 I1 equals to V2 I2. So this is very important conclusion right now here, because this shows that when the transformer operates, this primary winding VA and the secondary winding VA both will remain constant throughout the operation of the transformer. So now on this behalf, this is the overall operation of the transformer at full load. Now we will go for the we will draw the phasor diagram of the transformer at lagging load. Lagging load means basically we are considering that the load which is connected on the transformer, that is of inductive nature, and as you know, we had discussed in the class most of the time that most of the loads are of inductive nature. So whenever we are considering a general load, we will consider that one as a inductive load. So therefore we are considering this as an inductive load, and you can see the phasor diagram here. This is basically the extension of the no load phasor diagram. So in no load portion we had drawn phase flux, then on the same line a no load current, then EMF induced E1 and E2. Now in this portion, since we connected load on the secondary side, so current I2 is begins to flow through the circuit, and this current I2 we are showing like this because it is lagging behind the secondary voltage E2. So this current I2 is lagging behind this the voltage E2. So, and you know, I2 equivalent to I2, and in the opposite direction there would be current I1 dash, and this I1 dash will be nothing, it will be N2 I2 over N1, and this is the net I1 dash. And in the primary winding there are now two currents flowing. One is the no load current as well as the load component of current I1 dash, and the phasor sum of these two current will result into the primary current. So net primary current, this one is shown in the phasor diagram. That is basically the parallelogram sum of I0 and I1 dash. Now moving toward the real or the practical transformer. Now this one was the total portion which we understand with the help of the ideal transformer. First we understand the EMF equations, and then we understand in the second portion we understand the operation of the transformer at no load and at the full load. So with the help of those, we drawn the phasor diagram and we understand each and everything. Now with the help of this portion, now we are moving towards the real or the practical transformer by inserting the conditions which we had considered at the time of ideal transformer one by one. So now the first condition which we are going to insert or consider is now that the primary and the secondary winding will have resistance of R1 and R2. What would be the impact of it? We will see a little, please wait little. And the second condition, to compensate the leakage flux, we will consider that the primary winding has a leakage reactance of X1 and X2 inserted in both the windings. So considering non-linear BH curve results in the lagging. And now third condition which we are going to consider for the practical transformer is that the BH curve is non-linear, and BH curve is non-linear. It means you can see with the help of the BH curve, once the BH curve is non-linear, the current leads the flux by some angle that is called the hysteretic angle. So we will consider that case as well. And the fourth condition, once we will consider the BH curve is non-linear, there would be existence of the core losses. So we will consider here the core losses are no more 0 or negligible. Now coming to the phasor diagram which we had just drawn for the ideal transformer, the same phasor diagram we are going to draw for the real transformer with the condition of R1 X1. That is, first point says that primary and the secondary winding both will have the resistance of R1 and X1, as well as the sense there is now leakage flux. So therefore, to compensate the leakage flux, we are considering the primary and the secondary winding will have the leakage reactances of X1 and X2. BH curve as non-linear. So here in this phasor diagram, you can see now with the flux, this no load current is no more in the same phase. Now it is leading with some angle phi. This angle phi is called the hysteretic angle, and this one is leading. So why? This is because of non-linearity of the BH curve. And in the secondary winding, you can see this is I2 equivalent to opposite and opposite direction. There is I1 dash. Now the sum of I1, I0 and I1 dash, there is a net primary current. Now the interesting part which is here you need to understand is that now since there is E2 and V2, since primary winding resistance and the primary and secondary winding resistance and the leakage reactance, we are considering R1 and X1 and R2 and X2. So therefore we have to considering this one. So therefore we are considering, we have drawn this B2 over here. Why B2 have been drawn over here? Because we are considering lagging load. It means still the current is lagging behind the terminal voltage B2. So therefore B2 we are considering somewhere here, and the current is still lagging behind the applied voltage. So therefore we are considering like this. And then up to this place there is a V2, then from V2 this I2 R2, and I2 R2 will be in the same phase as of I2, and I2 X2 will be 90 degree lagging behind the applied voltage. So therefore this kind of the phasor diagram drawn, and the resultant of V2 I1 I2 R2 and I2 X2 will result into the E2. So this is the phasor diagram. While on the primary winding side, you can see this equivalent to E1, there is a one minus E1 dash applied. And then again, we are considering the impact of I1 R1. Of course, I1 R1 will be in same phase with the I1. So you can see this I1 R1, this I1 R1 is in same phase with the I1, and I1 X1 is 90 degree. I1 X1 is the voltage across the inductor. So therefore it would be 90 degree leading with the current. So this is okay. And resultant of this one. So we have covered up to this point. So now, okay. श्वेतांक,
Yes, sir.
श्वेतांक एक बार फिर से यहाँ से मेरे पास रिमाइंडर आ रहा है कि टाइम इज अबाउट टू ओवर, मतलब we have just few minutes pending.
Yes, sir.
So once again, I'm receiving this kind of notification. Therefore, I'm ending this class right now.